the presentations, you learn something new even in basic presentations, but the hallway track is just indispensable.
So hello, and I'm Kris, and welcome to the talk about the testing, where the future becomes the present. So I was having a dream for a while, how awesome it would be to be less dependent on a preprocessor. I don't know how many of you likes the C++ preprocessor. Oh, there's one person. I'm not going to ask about the reasons. I believe that it's a pure evil, just because it just takes substitution without any semantic meaning, and it's really difficult to deal with the results of it. So, while having that dream for a while, one day I realized that C++20 actually allows us to make that happen with the testing, one of the commonly used applications for the preprocessor. Unfortunately, all the well-known frameworks are using the preprocessor in order to do a lot of magic with the registration and other things. So I was thinking, can we actually get rid of it while it's not losing the functionality? Because obviously the functionality is important to be the same. And we actually can. And this talk is about that experiment. And hopefully you are excited as much as I am about it. So what we'll be talking about? We'll firstly talk about the motivation for the talk. And I briefly said about the preprocessor, but it's also about what C++ has to offer regarding the C++ framework unit testing framework so far. So we'll take a look into those. We'll try to implement a simplified version of the unit testing framework from scratch using the newest and greatest C++20, including modules, concepts, and other things. So hopefully that will be interesting and something to look at. For the, I said where the future becomes present, and that's it. And then we'll try to take a look into the fully fledged unit testing framework, which is used in the production already and has all the features available from the simplified version. It's basically how far we can push the envelope in order to get and how we can get, where we can get with that. We'll take a look into benchmarks regarding compilation times and run times and binary size and other things regarding the frameworks available currently, because it's, although unit testing, the performance is not as important, but if you have tons of tests, in the end, if you spend a minute or 5 seconds running them, it's important because the iteration has to be as quick as possible. And we'll sum it up. So I hope that makes sense to you guys and girls. Like, take a look into some learnings. That's kind of common across my slides. Usually when there's something on the background, something to remember. Since we'll try to achieve something, we'll get a dopamine boost by having a green background. Red-green refactor, that will be the green part. We won't have the red part because red part is actually currently the present as we speak. And everything is, runnable on the compiler explorer and available during the talk as well. The whole implementation as well as the framework is available online. You can try it out. So what's the motivation? So the motivation is to be able to run and easily test this function, a function of sum, which just takes variadic arguments and just sum them up. Simple. How we would do that these days without any frameworks? Well, probably we would make a comment and an assert or something. That's the only primitives in C++ at the moment which we have out of the box. I wouldn't do that. That wouldn't work in the release mode, for example. It doesn't scale very well, so that's the motivation for not using pure C++ for testing. We can do better. And that's why we have the problems with those solutions. We cannot list the tests. There's no useful information when we fail. It's hard to scale that at all, right? It's like test a comment. They just work in their debug. Easy to make mistakes, like the implicit conversions and everything from C legacy will be here as well. Hard to follow TDD and BDD, like good practices with just pure C++ and others. So that's why we have other solutions already. Google Test. Who is a huge fan of Google Test? Most of the audience like Google Test. I like Google Test as well. Boost Test? No one. Catch? There's some hands. Dog Test? Anyone tried this one? No. Others? Oh, disappointing. No, just kidding. That's the present. So yeah, so just for the recording, the Google Test seems to be by far the most popular solution. And with the good reasoning, I guess. But what's the problem with the Google Test and other solutions at the moment? And the problems will be generalized because obviously it depends on not all of the frameworks have the same problems. But mainly what I'm concerned about is that they're macro-based. That's what we're trying to fix here. The macro-based part has some benefits of, being easily expressible. However, the text substitution is the issue here. We don't really know what we get when we actually write test case, for example. There's a lot of boilerplate with some of them when we have to register stuff. Like Google Test by default has a lot of boilerplate when you have to create a class. And therefore I actually written a JUnit. I don't know whether anyone has seen that. It's a wrapper for Google Test, which allows to get rid of a lot of boilerplate. They're slow to compile, some of them. We'll take a look into that. Hard to integrate sometimes with, debugger or any other solutions. It's like when you have a macro, the debugging is quite difficult sometimes. And there are obviously other issues. That's the main issues I try to resolve in that experiment. And hopefully I will convince you that I manage somewhat, at least. So what's the future and current present? No macros, we can do that. Minimal boilerplate. Lambda-based minimal boilerplate. A bit, but still less than potentially we could have. Minimal learning curve, simple concepts, not a lot of them. Easy integration, one header, one module, just import it. Flexible and scalable. There's loosely coupled, easily to integrate. Not much to be worried about. Fast to compile and execute, and don't take that for granted. We'll take a look into the implementation and also the benchmarks. So what's the goal? So the goal is to be able to write this code with C++20 and make it runnable and get the outcome as desired. So on the first line, we'll just import the framework. And after that, on line 6, we define the test. And on line 7, that will be the expectation. There are different ways of doing that. We can also write an expect of that expression. But that's the simplest way of achieving the implicit assertions. And here, notice that we use _i, which allows us to get the number and also prevents us from having any narrowing conversion or anything like that. If types do not match, framework won't allow you to do that. You have to be explicit. And in the end, we'll get the number, the line, that it failed, why it failed, and a summary. So I hope that sounds exciting, or at least looks good, and maybe that will be the future. The other thing which we will do, since we'll have the primitives, we'll try to implement catch2 on a slide. So we'll make that code happen. Sorry, I didn't use Google test. Picked audience wrongly. But we'll do catch2. The basic functionality, obviously, I don't claim that I'll be able to implement the whole catch on the slide. But the idea is here that if you have the primitives available without macros, any macros we can write very simply to implement any framework. And that gives us the ability to quickly switch, easier switch between frameworks. So imagine that you really like what I'm presenting here and you want to use this framework, but you have all the tests with catch. So you can start, by writing the new tests in the new way and just provide the backward compatibility for the old test, which still will run with the macros. And you still have just one framework because, the worst thing ever is when you have partially baked solutions. So some tests are in this framework, some in the other one. You don't want to be in that stage ever. So implementation, let's take a look into that. Are there any questions regarding what I said so far? Sounds good? There is a question.
It said import, or we're using Boost UT. Is this part of Boost, what you're presenting? Or?
Great question. We'll get to that. And the question is whether the framework is part of the Boost. It's not. It's using the Boost namespace. It is because that's the way you apply for the review. So it's kind of ready for the review, but it hasn't been reviewed. So it's not in the Boost yet, let's say.
Okay, but your goal is to get it in.
Yeah, the goal would be to get it in. Or if it's not, to get rid of the Boost namespace.
Okay, thanks.
But the simplified version, which we'll take a look into, the implementation, it won't have that namespace at all. It will be just UT. So let's take a look into that. So UT module, that's the way we would like to start, import UT. So how we do that? 10 seconds crash course about modules, export module UT first line, which will be module interface unit. We import std, and notice here that you can write this export import std in the same line. That means that you would also export it outside from the module, but we don't want to export std because that's only the detail for our implementation because we need the std to do some stuff. But we don't want to export it. What we want to export is the namespace UT, the V1 version of it, and it's been accomplished by putting an export on the namespace. Obviously, in the fully fleshed framework, we don't want to export the whole namespace. Probably we want to export the parts which are user-facing. But for the simplified version, that would be the easy way to go. I hope that makes sense. So then we can start from trying to implement that by writing this code. Import UT, and we can verify that the namespace is there. We'll compile it with those flags. So that's a header file, emit module interface. It's something which we pass to the Clang version. There are different options for different compilers. We produce this precompiled module file in that case. We link it and we run it. Nothing happened, but we have our module. That's actually not super simple when you try to start with modules. So I would say achievement unlocked, but not yet. So what about the modules? So the module interface unit is the module which starts with the export keyword. And they're very similar to precompiled headers. That's actually the way they implemented in Clang. So you get the same performance boosts across the translation unit as you would use with the PCHs. But the main, I think, benefit out of them is the fact that you can hide the implementation which you don't care about. So the detail namespace, it's usually what we do in the present implementations. It's like, and hope that users won't do that. But here we can actually say that detail namespace is not exported, so you won't have it. And that compiler will tell you, not documentation. And there is a claim that they will be faster to compile, and I agree with that claim. But not much faster than the precompiled headers, in our use case, at least. So what about the test? So right now we have this import UT, we have the namespace, and we would like to write this sum underscore test equals a lambda. So let's start from defining the concept for the test. What is the test? The test is something which requires the name, because we want to run and print what test we run, and in the end, which test failed. We say that it has to be printable, the result has to be printable, and the printable concept is defined as follows, that the O stream will just be able to print that. And it has to be assignable, because that's the way we do definition for the test. So it's underscore test equals a lambda. So this expression here on line first, on the first line, an empty lambda is something you want to assign into it. So concepts, if you haven't heard about them, are like type constraints. It's like documentation for interfaces, in a sense. We couldn't do much before to get really good error messages, unless we use like Svina kind of magic or TMP magic. And before concepts, we usually get the error messages from the library side. And that's always not friendly, because no one cares about our implementation, shouldn't care about our implementation really. They should care that they use it wrong. So they should get the error, users should get an error at the point of instantiation, not the point of execution, which used to be the case. And faster compilation times, that's arguable, depending on the solution. It's supposed to be faster to compile than substitution failure is not an error kind of solution when you trickery TMP into doing things. But in the wild, it's not necessarily true at the moment. But we still get better error messages than that. So, 10 seconds crash course towards concepts. The simplest concept you can implement, and it's called the weakest in a sense. It's auto, true, always satisfied, satisfies everything. And right now we have different ways of expressing the same thing by saying foo auto arg. So that's C++ anything. Auto here is like implicit template. There's no requirements on it. Satisfied always, right? After that, we can write requires of this concept. Always satisfied, because the auto concept is always true, but at least we can express it, be explicit, and explicit is always better, right? But maybe the syntax might be on the left and the right, doesn't really matter. And we can also put it instead of class or type name or struct in the template. That's quite handy sometimes. But the best way of doing it is this terse syntax, where we put a concept, and after that an auto, which is the template, and an arg, which is the parameter. So that's the syntax which we'll use across this talk. And it's still equivalent to all of them. So I hope concepts make sense. They're really handy, and all those syntaxes are equivalent. in that case because the auto is always satisfied. That wouldn't be the case if the auto was something else. So okay, so we have the test concept. Let's write implementation for it. So we needed a name. String view name would do it because it's the compile time thing either way. We don't have runtime names for tests. And assignment operator, and here is this invocable concept, which means that something has to be invocable, like a lambda, right? Which we pass to it. It returns nothing. We'll print running the name with the simple implementation. And we will also run the test, which is the lambda, which we pass as an invocable. And then we implement this user-defined literal for the test, which will just return as an object with the name. So that's the UDL which we can use. And notice here that we use the concept as well on the return type. So we have concept, test, auto. So that's the way you can get the concept name, constraint on the return type as well. So right now we can write this. And if you write that, we'll get running sum. So right now we have tests. They are still in the global scope, and that's where we actually finish our simple implementation at, but we'll take a look how to do the regex kind of part of it with the registration in the fully fleshed solution. But so far, so good. So we have a lambda expression, which is empty at the moment, because usually testing is about two things. One is the tests. We have to register all the tests, run some of them, or basically all of them always. And the assertions, which we'll take a look into in a second, which are the verification of our assumptions. So far so good. Are there any questions regarding where we're at? No? Let's move on then. So right now we have the assertion to implement. So in that case, we have this equality operator being overloaded, in which on the left side, we will have our test, sum, 1 and 2, should return, that should be a 3, equals to 42_i, which is an int, because the left and the right hand side has to be the same type. And if the values are the same, we're okay. If they are not, we would like to bail out. And you can also imagine here that you can put expect on it. That's also valid. So we can write expect sum 1, 2 equals 42. And that has some benefits regarding the, like expressing your assertion. But that's the simplest way of doing it. So operator overloading is a bit difficult because we cannot do it for everything. Built-in types, if they are both on the left-hand side and right-hand side, that would be an issue. So if you want to overload, in our case, 2 ints, right? If you want to overload operator equals for int and int, we'll get the error that we cannot do that actually. And sorry, it's like, if it's not visible, it says that the overloaded operator equal must have at least one parameter of class or enumeration type. So in our case, since we use 42_i, which is quite handy in our case, one of those might be this type. And that's the type, integral constant, will give us the ability to overload it. So that will work. So if you have equality operator with a type and an int, that's okay. Otherwise, if you just have built-ins, that won't work. So let's implement the concept operator equal. First, it will take left-hand side and right-hand side, which is the sum on the left-hand side in our example and the 42 on the right-hand side. Both of them have to satisfy the operator concept because we don't want to overload it for everything. We have to be constrained here. And the concept will look as follow. So it will require left-hand side and right-hand side so that we can convert them. And it will have to be convertible to bool because that's what the expectations are about. Or on the other side, it might be an integral constant kind of thing, which has the value type and the value so that we can compare things. I hope that makes sense. We'll take a look into implementation of equality in a second. So equality will be something which we pass the left-hand side and right-hand side into. So how the implementation looks like, a simple class takes two templates, has a deduction guide. To satisfy the concept, it's a public LHS, RJS for us. And in the destructor, if it's not if the conversion to bool of ourselves will be true, it will be false, we'll go and report the error. And the conversion is actually where the magic happens. And we'll take a look at what the value is in a second. So we compare for the equality what the values are. And also we provide this operator, out operator in order to nicely print. And in the fully fleshed solution, we also print the colors because you can compound the expressions, like say 42 equals sum and something else. And then the expression which is satisfied will be green and the other one will be red. So here all the magic may happen. What about these details which we talked about? The error itself will just print failed and the expression will print the values and the comparison. And the value will just get the underlying value. And here we'll use design by introspection to verify whether we have a value. A value will be something which has the integral constant, for example, has a value. And our equality operator itself doesn't have, if you have the compound statement. So that's the nifty trick in C++20. If consexpr requires my favorite feature of C++20. So design by introspection is something which we just described, and we can easily verify that by, and the main benefit of it is that the branches don't have to compile. So v.foo is not available in the struct bar, but that's fine because it's consexpr requires. So we'll get to the second branch. Otherwise, we would just not compile and just get a hard compilation error, which wouldn't be what we actually want. So Andrei Alexandrescu, which is giving a talk at the moment as well, you can talk to him about that. Awesome stuff. So we have this assertion right now. What will happen if... but the only thing which I'm missing is this _i, which is the integral constant. And unfortunately in C++20, we cannot do, like the return type cannot be what we want. We have only those options available. So if we write that, let me read the error. Invalid return operator parameter type int, did you mean unsigned long? So you cannot do whatever you want. It has to be unsigned long. So you cannot figure out what you passed through and get the different return type with that solution. But there is an operator which takes char ... as a string kind of thing, and you can parse whatever it is, and that will be like 42. And how will we parse it? For example, that's one of the solutions. We call this lambda, get the numbers, and that's a simple solution to get the ASCII representation of the number into actually an integral constant as a number. So we do the power of -0 ASCII to get and sum that up. So if we call 0 underscore I, we'll get 0. If we call 42 underscore I, we'll get 42. So that's a very simple solution of getting the proper return type, especially. So right now we can return an int here if you want. And underscore I, it's for the int, right? If we want underscore UI, that'll be for assigned int. And we use this nifty trick about unrolling, kind of about immediately invoked function expression. And that's very handy to do unrolling, for example, as well, when we can specify a function which is supposed to be unrolled in that case, and then the assembly output will just, unroll the function and call it twice in place. So it won't be a for loop or anything like that. So in our case here, it will just put the CppCon text twice, which is pretty handy. And that's something which we couldn't do easily in one line before C++20. But that's possible with the making the sequence and the angle brackets after the capture, which takes the parameters and expand them with the default expression on the following line. So you have this assertion right now, but it doesn't say the file and line. So we're almost there. At the bottom you can see that it's 3 == 42. Almost there. Failed. Great. But it's missing the file and line. And that's the killer feature from C++20, source location. Thank you for that. It's a basically macro-free replacement for file and line and function. Awesome. Almost awesome, I'd say, because, well, operator equal cannot take it. So parameter of cannot have a default argument. So we would like to have the source location from the equality operator when we have the assertion, but we cannot do that. Sorry. That's disallowed by the standard because the equality operator has to take 2 parameters only, and it cannot have any defaults. So, well, simple solution, we can put it in the equal constructor. I notice the file line would be ut hpp, let's say 128. And then we pass the location into the error, and the error prints the location, file name, and line. If we do that, any ideas what will be printed? Do we get the line 7? Yeah, exactly. We'll get the ut hpp 128, which was from our implementation. Because the callee side on line 7 here doesn't have the source location. It's the implementation under the hood, which has the source location information. So we have to somehow move the source location into that part where we actually call it. So one way of doing it is by having the location into the constructor of something which is part of, oh, thank you for that. It's fully charged. So we have a value location, which also takes the value, it's a wrapper for the value, but also takes the source location. And then our operator equals, instead of taking just the template, it also takes value location. So the type detection here will happen. And notice the value type has to match, so that's also good for us because the right-hand side have to have the same type as the value location, which will be deduced. So in our case, int and int. And then we pass the location from the left-hand side here into our error message in our struct. And we'll get the right error message, the line and the file. It's because the callee side here will have the value location, because the constructor of the value location will happen at the callee side, not at the implementation side. So that's a trick which we have to do, unfortunately. If the operator equal allows us to do the default argument for the source location, we would be done. It's the same if we approach it with the expect. That's a function, we can put the source location there as well on the callee side. But if you just want to have this equality operator, we cannot do that. So then, if you do that, we'll get line 7, sorry, not line 5, printed into the error message with a failed and everything. So I would say achievement unlocked. Good job, everyone, by staying tuned. A bit of dopamine. So, any questions to what we've seen so far? Still exciting? So, just a bonus quickly to do the test suite. Obviously, just a test is not enough for us. We want to do more. For example, test suites. And we want to additionally use expect because not everyone likes or is familiar with this syntax that we just have the equality operator. It's arguable, confusing sometimes. So let's implement expect. First, we have the import UT already. Expect is very simple. It takes something which is returning something which is streamable because we want sometimes print an error, like in Google test, you can stream expect into something, expect assert. No, expect equal or assert equal. You can stream into a cout, for example. And we take the expression, and also here notice that we can take the location because the expect is a function and we don't have limitations on default arguments. The expression itself is something which is printable and convertible to bool because we have to verify whether it's satisfied or not. If the expression is satisfied, we return. If it's not satisfied, if it's not true, we return an error with this location. Otherwise, we don't do anything, and we return the error in that simple implementation. So what will happen if you do that? We get the error as expected as well. So that was actually even easier than the implementing the operator equality. The suite is the simplest thing ever because in the constructor we just pass something which is invocable because that's what is the concept of the suite, and just call it the same like with the test. In the fully fleshed solution, we would register it here and call it later, but in our simple implementation, we'll just call it here and call it a day. So then, if you write that, notice that wherever you assign it, we will call it. So the first, line 3, will be assigned to a constructor of the suite, and we'll call it immediately in the constructor. The constructor will go through all the tests, which in the assignment will also trigger to be called, and then expect, in that case, will match all the requirements. So the full implementation can be found on GitHub, and you can also experiment with it on Godbolt and also on Onebox. Right now, actually, we could do that on Godbolt with the CMake stuff, but back then, few weeks ago, we couldn't do that with the modules. So right now, the Onebox solution allowed us to do that. So the module part is there. Are there any questions regarding the framework, the simplified implementation of it? No? So let's take a look into the fully fleshed solution. What we can actually, how far we can push this envelope and what we can get out of it. So overview. It's C++20, surprise, surprise, but it supports 4 compilers, including MSVC. It worked on it. 2019. There's some limitations because the source location wasn't part of it, but 2022 definitely will have it. I believe so. So the source location will work out of the box as well there. It's single header, single module, 2000 lines of code, no external dependencies besides the STL. It's macro-free, and that's the goal. And it has all the features which you can think of in the testing framework: assertions, suites, tests, sections, BDD support, matchers, login, blah, blah, blah. Back to your question, it's not official Boost library. Potentially maybe in the future. So hello world, you can click it. You can see the similarities to what we already have. But what is pretty cool about it is that the print on the bottom, you can see that 3 is greater than 0. That's green. And 41 equals 42 is red. So you can, it has, these compound expressions on line 11, but also it prints it nicely. And there's a summary at the end. And yeah. And you can either import it or include it, depending on what support do you have. But it's still the same file. So how the main looks like, you can filter obviously, so that's the run kind of call when we override the filter from the command line arguments. We don't have to do that if we don't want to. All the tasks will be run by default. But if you want to do that, then we can simply also use the regex to run the specific tests. So if we do, in that our case, we assign the filter to the first argument of the command line. So if you pass the single, it will just run one test, single test. By default, with the star, we'll run all the tests. We can also do the subtraction. So many.equal star will run one test because of the subtests. Nothing special here, just the regex for running the tests. We can do tags as well. So you can imagine that you have a performance test or skip test or something like that, or nightly test. So you have a test which you would like to tag with something, nightly or slow. That's a common case. Or the test which you unfortunately don't want to run for a short period of time because you started to do, like you were doing BDD and TDD at the same time. And when you want to not run the other test for the second and come back, you can just skip it. And then you can also override the tags by saying the tag equals. The command line, there's like no define, like there's no, UT doesn't have the command line parsing or anything like that out of the box. So you can use whatever you want out of it. But the simplest part, just assign the arguments from the command line. And in that case, all the tests passed, one test is being skipped. The beauty of the framework itself, it's the fact it's really composable and flexible. Everything can be changed. The printers, reporters, formatters, everything might be, it's just a type and has to satisfy some concepts for the reporter or runner. So it's really easy to change. So for example, adding parallel execution is super simple. We just have to override the runner for it with the proper implementation. Assertions. So there are different ways of doing it. The test syntax, which we explored a bit, doesn't need expect. It will print failed with the colors. We can write expect with the same syntax. We can say expect that and then notice that we don't have to specify _I if you don't want to. So that's handy to do the macro thing. That's the way, catch is doing require. And when you don't have to say _equal, _not equal stuff. So that's the way it's been done. You just overload an operator with the priority lower than the expression. You can also have the fatal expressions, which are like assertions. when you have the size and you don't want to, go further in the code afterwards, you just say fatal, and the line 3 won't be executed here. You can also do floating point and compound expressions as well. I notice here that the granularity, how it will be compared the floating points, depends on how many zeros you can put at the end. You can also say it explicitly, how much narrowing you want, but in that case, you just care about the 2 because you put this 0 at the end, which wasn't really needed. So if you put 42, 1, 0, 0, 0, 0, 0, that would be like 4 or 5 places you want. But you can also be explicit and say approximately with that value. And the colors are still there. And string views will be printed nicely, as you can imagine. There's a question?
I just thought there might be a typo on that last example. It says 41 in the code, and the green text below it says 42. Is that like a typo?
Yeah, that's a typo. It's a good point. So the comment here was that there is a typo on the bottom of the screen, 41, 10. Yeah, it does. Yeah. The framework is not that smart to to figure it out yet. Like I was saying about the present, but maybe we should talk about AI future, where we actually, use Copilot to write our tests and make them pass. Maybe next time. But thank you. Good point. You can also print, and when it doesn't match, obviously, if it matches, it won't print it. So you can add nicely things. You can also do that with the expect, nothing special here. If you really want, you can log. I wouldn't advise that because, if you have to log, it means that your test is doing too much and you probably should refactor the test because you don't know where you're at and what's happening, and tests should only test one thing. So if you're unit testing, and that's the unit testing framework, if you have to log or step, it seems like your design probably haven't been driven by TDD, at least. You can have sections, which is super cool feature from Google Catch too. Google Test doesn't have it, GUnit has it, if you want to check it out. So we have the setup. Then we have the shoot, for example, here, which is basically, you can also write _test if you want, but shoot is more expressive in that case. You have, and how does it work? So we have a setup. After that, we have the shoot first test, the free kind of part of it, and the second shoot won't be executed, and we have the tear down, and after that, we'll go again. We'll do the setup, the free part of it, and the section 2.2, and the tear down. So that's really handy to write different tests and with the setup and tear down without repeating yourself. So that's really handy. Andres, you want to take the picture? Cool. Question?
Yeah. So is the setup run between each test, and is there a way to have the teardown run after each test?
Yes, by default, after each test, teardown will be run.
Okay, so the
Do you mean
teardown.
each section or each test?
Oh yeah. That's,
Just clarify your question, sorry.
I meant between each test. There's 3 tests there, right? Or
two.
There's 2 shoulds, and then there's a test in the middle, I guess. So does the setup run after the first should and before the payload?
Yeah, so here it's actually 2 tests, which have the should.
Right, and then there's an assertion in the middle.
Yeah.
So where does the setup run?
The setup run for the first should. You mean whether there's another test which doesn't have any should clauses in it?
No, like, will it set up the vector v with 5 after the first should and before the 5 ul equals std size v? Does it run it again?
No, it runs the test twice for each should. With
I mean, it can't run it again. This is just C++ code, right? You're just going from top to bottom. So it can't run it again. But I think what you're getting at is maybe it would be nice if it did, or maybe it would be nice if there was some construct that would do the setup and tear down for each section so that it's nice and clean, so that you wouldn't need this assertion to be repeated for the one that's tagged into comment 3.
I see.
Is that what you're getting at?
Yeah, I think so. Just setting up and tearing down between each test to avoid boilerplate.
I see, yeah. So that's not what is happening, but yeah, I see your point. Good point.
You could imagine writing something that does that and passes the sections as like some kind of container. And like the first argument, like the container is the second argument, the first argument is the setup, or something like that.
Yeah. Yeah, it's definitely, the comment here is that it's definitely doable, but it's not what is this example doing. But yeah, definitely open for solutions. That's just because this is taken from Catch 2 translation. That's what it's kind of, because again, wrong audience. Sorry. So what about the errors? For example, the test suite, you can verify whether it throws. And also you can verify whether abort. That's something Google Test supports with the assertion dev, I think. So also it's supported. And I will just run the tests. Whether you should test assertion is arguable, but it's supported because it was required for some of the projects people wanted to use that project for. The parameterized test, so that's pretty cool because you can actually add a test with the runtime name, runtime, like parameterized tests in Google Test, a lot of macros, instantiate _p, I don't know, I don't even know. Here, for loop, define me the test with that name, whatever, all test passes. You can also do it more explicit way with the pipe syntax. Like that, you can pipe it to a tuple, and then you have the types as well. So there's no magic here. It's just C++, which is cool. Template metaprogramming, why not? We wanna do constant verification in C++20. We can actually do that because we have non-template type parameters in that use case. So it will also print 42 not equals I. In that case, but not equals 0, but it will verify that whether that expression is actually at compile time. You can verify the types, and if you want to verify that the sum actually returns an int, you can do that with type equals int, and it will print, the types are not matching. Spec, it's something which is also supported. All of those, describe, should, all of them are just tests. The same thing. It's just a lambda. It's just different name on the lambda. So you can imagine the same test with describe and it syntax. Nothing special. You can do BDD if you're fan of that. Again, feature scenario given when then. It's basically the same lambda. So it's the same test written in BDD way. When you have a given feature scenario given when then. And you can simply follow that logic. It will give you the tests. You can also do Gherkin. Anyone familiar with Gherkin syntax? When you have, I see half the audience. So the same feature might be written in this Gherkin syntax, kind of thing, like a cucumber, which has the benefit of the fact that it's written by the idea is that your product owner or someone who gives you the requirements gives it to you in plain English, and then you can implement the backend for it in any language. So you can imagine that you can have the feature which will be backed up by Python for the binaries and backed up by C++ for libraries. So you can do that. In that case, you have to do steps, which are regexes to satisfy the given when then clauses, and we'll just run them in the end by parsing the feature file and going through the feature file and running the steps accordingly to what we have in that case. Parallel execution is something which is super simple as well. We just override as I pointed out before, it's very flexible. We just override the runner with the parallel runner, and that will be executed in parallel. Nothing really difficult here. Parallel runner, you just have a run function, and I don't have implementation here, but it's like 10 lines of code. And much more. There's much more if you want to explore it. It's on GitHub, available for you to take a look. And are there any questions regarding the fully fleshed implementation of UT? That's a question.
Clarifying question. The tags looked like they were like connected by forward slashes, or so like tag is not a keyword, but it's like a function or a free-floating function or something.
Yes, tag is an object which takes the name. Okay. And then you can.
Last forward slash just combines it with the test.
Yes. The tag might be combined. A really good point. Either with another tag or with the test.
Yeah, are there examples on there of doing like custom matchers for like your own types? And second to that is, can you compose all the matchers? So like, greater than 5, less than 3, and a whole list of things.
Yes. So the question is whether you can combine matchers. Yes, you can do whatever you want out of as complex as you want. And it still should work and print it nicely. So, if there are no more questions, let's take a look quickly into benchmarks. So I try to benchmark all the frameworks which are quite popular, including Google Test and Catch too. I try to put, it's like obviously that's not, definite benchmark or anything like that, but I try to use the configurations which are described by default. So what is available, what documentation says, you should try that. So the include file, you can see that Catch 2 is quite slow to include. Google Test is really good as well. UT is actually even faster because there is no match. And that's about the header file. If we have the test in which we have 10,000 tests, 20,000 asserts, and 100 CPP files, and that's from scratch, and we use the test suites and asserts, and STL is involved. You see the pattern here that there are frameworks which compile slower than the others. So regarding the compilation, depending on the compiler, the fastest to compile are DocTest and UT, and the slowest, I would say, BoostTest. Google Test is like in the middle. But you can see that the difference is quite huge because that's in seconds. Execution, Google Test, fast to execute. UT, fast to execute. Catch, really slow to execute. BoostTest, slow as well. And the binary size, which is not that important, but it's also huge in BoostTest and Google Test because of the static library, I would assume. And that's the main, the most important benchmark, in my opinion, incremental build, because that's what we usually do. We start, we don't recompile all the 100 files, we just recompile one file because we change the test or change the implementation of something. So that's where Google Test is not as good, unfortunately. BoostTest as well, and you can see that the patterns like DocTest and UT compiles really fast. And the execution, again, Catch is slow to execute, and BoostTest. Just a side note that the headers versus precompiled headers versus modules. Headers are slower than the precompiled headers and modules and precompiled headers are very similar in the results because they're backed by the same underlying PCH implementation. But the point here is that headers are slower than the modules, let's say. So to sum up, because we're running out of time, C++ enables a cleaner design and implementation. I think that's kind of proven by the framework. Qt is an example of cutting-edge unit testing framework. I believe so. Not biased. Whether we should standardize primitives is an arguable question, which I'm not going to ask here. And we can build all the macro-based frameworks on top of those primitives. And I promise that. So let's take a look. 3, 2, 1. That's it. And that's the implementation. As you see, require, test case, and section might be implemented in expect and test very simply. And if you run it, and we'll get the results immediately as expected with the syntax very familiar to catch to developers, users. And the same might be implemented with the Google test as well. So yeah, let's finish with the saying, if you like it, then you should put a test on it regarding testing. Thank you.